So kind of like what is economics? If you ask somebody what's econometrics, you'll get a lot of different answers. You know, people say it's the application of statistical methods to questions having to do with economic phenomena, right? There's a lot of different definitions. That's generally the idea. So we're using sort of statistical tools that are actually have links to or are things in common with, or in some cases are the same as the kinds of tools that you'd see in other fields that use empirical methods, other social sciences such as political science and sociology, some medical sciences like epidemiology, and then some natural physical sciences as well, and a good example is ecology. So some of the kind of regression-based methods that I'll talk about today may be things that you recognize from your own work or work that you know of in one of these fields. And what do these things have in common? Well, they're fields in which we value the experimental method, right, the sort of scientific method. We like to use experiments when we can, but we're almost always, or at least often, stuck with using observational data to evaluate hypotheses of interest. And so we have to figure out ways of trying to tease out, right, sort of an almost or a quasi-experimental result from non-experimental data. So there's a long history of this in economics, right? So you can go way back to people doing empirical work where they had rooms full of graduate students, inverting matrices by hand, right, at their desks. And all the way to now when, I can literally from my Mac desktop, I can run, regressions using, 4.5 or 5 million observations. And it's a little slow, but not that slow. And so things computationally have changed pretty dramatically. But things have shifted in terms of kind of the way we think about causal inference in econometrics even more dramatically. And this has happened in some other fields as well. In fact, a lot of the methods I'll talk about today are methods that we at least initially borrowed from other disciplines. And I'll talk about those disciplines as well. But people talk about this as, Josh Angrist and Pischke have talked about it as a kind of credibility revolution in econometrics or in empirical economics since maybe the 1990s, maybe somewhat earlier than that. It's hard to kind of date the actual shift. But what they mean by that, and this phrase kind of taking the con out of econometrics, is that it used to be pretty feasible to sort of make a career in empirical economics publishing results that were pretty clearly just associational in nature, right? So, what is the link between the minimum wage and the level of employment, or, sort of what is the impact of, a tax on consumption or something like that, where we knew that we had questions about our ability to draw causal inferences from those models, and yet we sort of said, well, this is observational work, and, it's not an experiment, so we're kind of doing the best we can. And I think that has changed, again, quite dramatically. So the credibility revolution really has to do with focusing on having very sort of high threshold for, a high standard for this focus on causality and identification in using observational data. So what kind of a toolkit are we talking about? Sometimes we're talking about randomized experiments, as Pete mentioned earlier. It's not very frequent that we see these, but this has also changed pretty dramatically as well. So someone mentioned earlier that in development economics, experiments are more and more common. It's true in environmental economics, and in fact, all fields of economics as well. So I'll talk about some examples of that in the environmental realm, and what we can learn from those. And then there's a whole set of sort of observational methods, regression models with kind of flexible sets of controls, often very large sets of controls that deal with any potential kind of confounding sources of variation that you think might mess up your ability to draw causal inference from your regression technique. Instrumental variables models, that's something that was discussed in the readings assigned for today for the analysis of real and natural experiments. I'll be clear about what I mean by natural experiments in just a minute. And then difference in difference type strategies that use kind of repeated observations on the same units, households or firms or some other entity over time to control for these kind of unobserved omitted factors that we think might be confounding. So I really like the 4 questions, the sort of 4 research design questions that Angrist and Pischke set up in the article that we read for today. So first I'll kind of run through those and as just a way of thinking about empirical problems, and then we'll kind of dig into the details on some of these particular methods. So the first question they say is, what's the causal relationship of interest, right? Just give me a well-defined research question. Okay, how does an Endangered Species Act listing in the United States affect a species' survival probability? How does information disclosure about drinking water violations by your water utility affect the rate of those violations among utilities? Do protected areas reduce tropical deforestation? What's the effect of air pollution regulations on mortality? Does spring protection or the protection of source drinking water, reduce the incidence of waterborne disease in households? So these are all sort of questions and sets of questions that have been asked and answered by empirical economists using the kinds of methods that I'm going to be talking about. Again, sort of some of them coming up with answers that are more convincing convincing than others. And I'll mention each of these studies as we go through the discussion. So their second question is in some ways the most important, right? It's the most important, in some ways, point of departure, right, from, between people doing empirical work in economics and people doing empirical work sometimes in other fields. And that is, they say, you have to think of yourself as designing the experiment, right? What's the experiment that you could design if you had an unlimited budget, no, sort of restrictions on sort of morals or ethics into how to conduct research? If you could do anything you wanted to, what would be the experiment you would design to test that hypothesis? And one of their fundamental points is that if you can't design that experiment in your head, right, it is sort of fundamentally undesignable, then you might as well not sort of empirically investigate that question. There may be other things you might want to do, some interesting descriptive work or something, but you're not going to, right, you're sort of not going to be able to do anything with observational data that you sort of clearly couldn't do in an experimental setting. So that's the first thing, right? Sort of put a filter on that helps you sort of maybe be a better selector of good research questions. And they give that nice example, right, of the Paul Milgram study, right, where he, by standards that would be unacceptable today, engaged undergraduates in an exercise in which they were delivering shocks, right, to people in a psychology experiment to understand, right, how people would react in that kind of environment. We wouldn't do that, but you could still kind of at least go through in your head, right, what would be the potentially unacceptable, right, i.e. hypothetical research design that you would use to test your hypothesis of interest. All right. The third question is, what's your identification strategy? So if you're at an economics conference or in an economics seminar, right, almost always if there's not a slide that says identification strategy, right, someone's first question is, what's your identification strategy? So this is a very common question in this context. And what we really mean when we say that is, how is it that you're going to use your observational data, right, your data that you're collecting through some non-experimental method to approximate a real experiment? How can you try to kind of squeeze out of this observational data something that is closer to what we would get from an experiment? And often that hinges on your ability to construct with those data some reasonable counterfactual. Okay, and I'm going to get into more detail on what's a reasonable counterfactual in just a couple of minutes. And then finally, a question that is important to the statistics, but a little bit less important for kind of getting your good intuition around the experimental design is, what's your mode of statistical inference, right? So what's the population to be studied, the sample to be used, what are the assumptions you're going to be making when you construct the sort of standard errors around your coefficient estimates? And we can talk about that later on if people have questions, but for the most part, I'm going to sort of leave that step 4 out of the discussion for today and really focus on steps 1 through 3 in terms of just purely thinking about those early stages of research design. All right, so what do I mean by a good counterfactual? So really the underlying problem that we're trying to tackle when we're using observational data, right, to test a hypothesis is we don't necessarily know. So if I want to know, what happens when I list a species as endangered under the Endangered Species Act? Does it eventually end up doing better or doing worse? Okay, so and this is an example, sort of a thought experiment that I'll carry through the discussion, and ultimately we'll be talking about a paper that asked just this question by Paul Ferraro, who's at Johns Hopkins, and some of his colleagues, where they use some of these sort of modern econometric techniques to ask this and answer this question. So here I want to know, right, if I'm listing species, am I doing harm, am I doing good, or is this neutral, right? What's the impact ultimately on their survival probability? So what if we simply compare outcomes? Okay, well then I've got 2 populations, right, one listed and one not listed, and the concern is that if I observe a difference in outcomes post-listing, right, for some of those species, that what I'm really doing is I'm combining both the average effect of listing on survival and some selection bias, right? Something that was special about those species that got listed that could make them either more or less likely to survive. And so that's kind of going to be mixed in, right, with the estimate of the average effect of listing when I go ahead and I look at just observational data on species that were listed versus not. Right, so the underlying story here is I'm worried about selection bias. I'm worried that these treatment and control groups, right, the listed versus the not listed species, are going to differ, right, in some ex-ante way, right, that has nothing to do with my experiment, due to factors that also affect the policy or program's outcomes, right, the effect of listing. So one story would be, maybe listed species were really sort of at the desperate moment, right? They were less likely to survive than the species that ended up not getting listed. And so I list them and I see worse outcomes for those species. Well, my estimate is going to suggest that listing was bad for them, but really it was just the bad, sort of worst off species that ended up on the list. Okay, so that would be one story, right? That would sort of suggest a sort of negative direction for my selection bias. But I could also have another story. Maybe listed species were more likely to survive, right? An agency was thinking, well, I think I could actually do something about the survival probability of this species, so I'm going to list it. And then again, I have going the other way, but I still have this problem of selection bias. And in either way, right, whichever way it goes, it's going to get mixed in there if I just use this observational data on listing to understand the impact. Okay, so in this case, right, any kind of pre-listing difference in species survival probability between the control and treatment groups is going to sort of mess up my estimates if I go out there and just run a regression, right, that sort of regresses survival probability on whether you're listed or not. So that sort of problem of selection is really the kind of fundamental problem that we're trying to deal with when we're trying to construct, right, some kind of experimental design or quasi-experimental design using observational data. Okay, so let's take a step back and we'll say, well, what about experiments? Okay, so there are definitely environmental economists who do experiments. Why do we do that? Just like in any other field, right? That random assignment of observations to control and treatment groups can solve the selection problem. Okay, so randomized experiments just in our field, just like in others, are sort of the gold standard in empirical analysis. If you really believe in that randomization process, right, and you get that right, you can do a really nice, very simple, right, analysis of comparison of means before and after, and so on. And until recently, there wasn't a whole lot of work in this area, right? Sort of experimental field experiments. There's a relatively long history of lab experiments in economics, right? Sort of pulling people in either for doing stated preference surveys or, right, some other experiment. We're trying to understand, you know, free riding behavior. You know, game theorists have used kind of lab experiments for a long time. But field experiments are costly. They're in some cases sort of, you know, could be questionably moral or questionably ethical. So a lot of concerns about doing these. And so there have been a lot of barriers to doing them over time. But I would say, again, sort of a pretty dramatic change in recent years. And I'll give you two recent examples. One was a paper in 2011 by Michael Kramer and some of his colleagues, where they were working with an NGO in Kenya doing sort of infrastructure type built protection of source water for households that were collecting water by hand. And the paper was called Spring Cleaning. And the idea was, right, I've got a budget for funding the kind of rollout of this spring protection program. And I can't necessarily just randomize, right, springs and just, you know, protect some springs and not protect others. But if I have a budget and I'm going to protect a certain number of springs, the researchers sort of worked with the NGO to randomize the rollout. Right, so I'm going to hit a certain number. Well, if you can sort of decide in some random fashion which ones are going to go in first, then I can study what happens as you construct these things, you know, to source water quality and ultimately to household health outcomes. And I can get over this barrier of, hey, you know, it'd be unethical to randomize, right, source water protection. And so they do this interesting study, and the question there is, so why would we think an experiment was necessary here, right? Clearly, epidemiologists have studied for a long time what's the impact of improving water, you know, source water quality on household health. Well, the concern would be that if you don't randomize, right, you might have some underlying differences between the sort of treated and untreated households beforehand that's going to cause you trouble with inference later on. So an example that they talk about in the paper is, don't we worry that if we protect springs, then households' own sort of compensating behavior, maybe they engage in less sanitation behavior, or maybe there's contamination in transport and storage, right? All of these other kinds of changes in behavior that the protection can afford may kind of cause me to get this bad estimate of the impact of source water protection. So they did a nice experiment. It's published in one of the top journals in economics that showed that there was a very significant improvement in sort of lowering fecal contamination of the source water, but that did not translate into large improvements in household health because of these sort of compensating behaviors and contamination in transport and storage. So that answers some very sort of interesting and important policy questions using an experimental design, which makes it a nice example to talk about here. Another one is a recent paper by Katrina Jesso and Dave Rapson in the AER that just came out a few months ago. And these guys, the paper's called Knowledge is Less Power. That's kind of title of the paper before the colon. And they say they work with a set of electric utilities in Connecticut, and they randomize the distribution of kind of real-time little devices that give households real-time information about their electricity consumption and their price. And the price varies by time of day in these particular electric utilities. So they randomized the rollout of these little devices, and then they looked to see whether providing that information to households about their real-time usage and their real-time price affects how sensitive they are to price changes, right? And it turns out the households that have this little device that they can stick on their fridge or their wall makes them much more responsive to these sort of temporary price increases that the utilities are implementing in order to encourage conservation behavior. Okay, so again, very nice kind of clean experimental design. And the statistical methods or the econometric methods that one uses to analyze experimental data are actually very simple and straightforward because you don't have to worry, right, about all of the selection issues that come up with observational data. So I could make a very long list of these now, these interesting experiments, and I'm happy to talk more about with folks about some of this literature if people are interested. Okay, but for most of us, experiments are not, at least not always, going to be possible or desirable. And so what do we do? Okay, so an example that I work with is I have a paper where I'm working with a colleague on whether, kind of what's the impact of being in an international river basin on your water damming activity or your river damming activity. Are you more likely to put dams on kind of shared rivers because you can pass off some of the costs to downstream riparians that you would otherwise have borne yourself if you put the dam on a domestic river? Well, I can't do an experiment on that, right? I can't get, the World Bank to spend a couple of tens of billions of dollars randomizing, right, funding for dams and then seeing where countries might choose to put them. I have to kind of work, right, with what I've got. And so now I have to worry, how do I design an empirical approach that tests my hypothesis in some manner that replicates as closely as possible that experimental result, right, the conditions of a controlled experiment. And the rules of thumb have often to do with kind of keeping the methods as simple and straightforward as possible. Again, that's a really big shift from where econometrics was going kind of back in the 1970s, 1980s, and even in the early 1990s. Right, that I shouldn't have a model in which the interpretation of my estimates is sort of heavily dependent on the model, like the functional form of that model, for example. And hence, so why do economists love linear regression so much? Well, that particular method is just incredibly statistically robust to a lot of things. It has a lot of drawbacks to it as well, but there are a lot of things that we worry much less about with linear regression than we do with other much fancier models. Okay, so even where earlier analysts would have worried more about the downsides to this class of approaches, it turns out, at least right now, we feel that the upsides of these things kind of outweigh some of the downsides. All right, so often you're kind of trying to be willing to trade fancy models for the robustness of simpler approaches. So I'll give you some examples of that in just a few minutes. And a lot of times, the methods that we're using are sort of circling around something called a natural experiment. So what do we mean by a natural experiment? Right? We know what a field experiment is, right? I go out, I randomize groups into control and treatment, I implement an intervention on the treatment group, and then I sort of look at what happens afterward to the two groups, and I try and look at that difference. A natural experiment says, I'm not going to conduct the experiment myself, right? But there may be something created by nature, by chance, some sort of exogenous policy shift that kind of did an experiment for me. And the classic example of this, or one classic example of this in the economics literature, is an experiment, a natural experiment that was exploited by David Card and Alan Kruger, looking at the impact of the minimum wage on employment, where the guys were sort of looking at, there was a minimum wage increase that happened in New Jersey, but not neighboring Pennsylvania. I hope I'm not reversing those two states, but it happened in one state and not the other. And they said, hey, look, there's sort of a line between the two states, and whether you're on one side or the other of that border, especially as you get really close to the border, is essentially kind of a random thing. And I want to look at what happened to employment in fast food restaurants that fell on either side of that border. And so they exploit this kind of the combination of the state border and the policy shift in one state versus another as a natural experiment in what happens when you raise the minimum wage. Okay? So I'm sort of looking at this natural threshold, barrier, policy shift of some kind, and I'm going to exploit the variation that's created, right, by these clearly delineated groups to estimate the effect of interest. So some examples in the environmental realm, there's a nice paper by Gary Leibkap and Dean Luke in 2011, and these guys are very interested in property rights and the influence of property rights on land values, okay, among other things. And so one way of thinking about property rights and how well they're defined is the system of land demarcation that's being used. And so what they do is they say, so actually if you own property on the East Coast, if you've ever sort of signed a title to a home, you'll know that they use a system called meets and bounds. Okay, so the original 13 states plus Kentucky and Tennessee use this meets and bounds process where, you know, your title to your land says, you know, you walk from the fence post to the post oak and then make a right and go. And so it's all sort of described based upon the land features, which can change over time and can create some uncertainty over where the boundary of your property is. Okay, so I've certainly had that experience in my home in Connecticut, and maybe some of you have had that as well. And then in the West, okay, so if you kind of go west of those original 13 states plus Kentucky and Tennessee, we use the public land survey system. So a very kind of, you know, very well delineated land demarcation system. And so these guys say, well, how does that affect property values? Well, I might be worried that there's some underlying, right, sort of difference between these states, and if I just go out and estimate differences across states and land values based on the demarcation system, that's going to get all mixed up with other differences between those states, right? Some differences, taxes, differences in, you know, sort of legal security of property rights regimes and so on. And so what they do is they say, well, you know, let's take Ohio, and in Ohio there just happens to be this group of counties that was sort of delineated under the meets and bounds system because it was donated. It was land that was donated to Civil War veterans, like ages and ages ago. It was called the Virginia Military District. And I can take within one state, I've got this sort of natural variation right across this boundary between the VMD and outside, and I'm going to look and I'm going to see what happens to the property values on either side of that threshold. Okay, so that's, again, where did the natural experiment come from? It came from this historical thing that should have nothing to do with today's property values, but for, right, this difference in the property demarcation systems. Another example of that was Matt Kotchen and Laura Grant have a paper in 2011 where they're interested in what's the effect of daylight savings time on electricity consumption. Okay, and they say, well, right, the original purpose of the thing was to save energy. If you go back to look at what Ben Franklin talked about in terms of daylight savings time and so on. And so Kotchen and Grant say, well, again, right, there are sort of differences across states that have adopted versus not, or even countries that have adopted versus not the daylight savings time process. And so they look at, we all know, or many of us know, that Indiana for a long time, right, had some counties that were under daylight savings time and sometimes some counties that weren't. And then in 2006, the whole state was supposed to switch to daylight savings time. Plus, we've had some changes in daylight savings time that lengthened, right, the time of the year that was considered part of DST. And so they sort of take this natural experiment, right? Who did the experiment? Well, not them, right? But Indiana kind of did the experiment for them. They said, okay, all of a sudden everybody's going to shift, right? And that decision, that policy decision, shouldn't have had anything to do with the relative electricity consumption in those two sets of counties. And so what they're going to do is they're going to exploit that shift, right? And plus the changes over time and the lengthening of daylight savings time to try and understand the impact on electricity consumption, okay? In case anybody's curious, what Leibkap and Luke find is that the sort of very clear property demarcation system increases property values, and what Kotchen and Grant find is that daylight savings time causes us to increase our electricity consumption, not decrease it, okay? Okay, so when we talk about natural experiments, that's often what we're looking for. And then on top of having a nice experiment to exploit, then you have to decide kind of what your methods are going to be. So some of these methods, right, I could use regression methods or IV methods or others to analyze the results of a natural experiment. Okay, so there's not sort of a fine line between natural experiments and these other sets of methods, but they're going to kind of merge in some ways. But when I'm talking about the sort of simple, straightforward regression models, usually what I mean is I'm going to take a model and I'm going to regress, right, some dependent variable on a set of independent variables, but I'm going to control as flexibly as possible for potential confounding variation, right, that could come in and contaminate, right, or bias my estimates of the effect of interest. And so typical models of this type would include sets of what we'll call fixed effects, okay? So sort of think about it as a standardized intercept, right? For every household, for every year, for every firm, right? Whatever it is, but whatever is the spatial and intertemporal source of variation in my data. And then I could add to that a sort of rich set of descriptive covariates, or sometimes I only see, right, the sort of simple sets of fixed effects, right, essentially bunches of dummy variables that I'm using to sort of sweep out all of this potentially confounding variation. And the idea here is that, you know, if I'm interested, for example, in a study I'll talk about in a minute, I worked with some colleagues at RFF looking at what the impacts of on water quality were of shale gas development in Pennsylvania. And in that paper, I would be worried about things like, you know, so one of the water quality indicators we were looking at was chloride. Okay, so what are other sources of chloride? Well, things like road salt. Okay, it's a big source of chloride in northeastern states in rivers and streams. And so I worry about that, but I have two different options when I decide how to control for the impact of road salt on chloride levels when I'm worried about, right, trying to understand the impact of shale gas development. One, I could go out and get the best data possible on applications of road salt, and I could build a complicated model, right, about the sort of movement of that stuff over time and space, and really try and control for it carefully in that way. Or two, I could say, well, what does road salt application and sort of making its way into water bodies vary with? Well, it varies over time. It's more common in the spring than it might be in the dead of winter. It might be more common in some places than others. And then I can put in, instead of sort of specifying a very specific relationship between road salt and chloride levels, I can just control very flexibly for, right, the sort of variation over time and space, and try and pick that up in those kinds of variables. So the idea is controlling for observable stuff isn't enough. Right? That I should also control for any potentially confounding unobservable heterogeneity. If somebody had a story to tell about a source of water quality impairment, right, that could potentially be correlated with shale gas development, I should be able to tell, right, a story back that says, right, I don't have a variable in here describing exactly that phenomenon, but I'm as certain as I can be that the variation that's associated with that phenomenon is not contaminating my estimate of the impact of shale gas development. So I'll give you some examples again. So for that particular paper, what we did is we had, right, there was sort of variation over time in the presence of shale gas wells upstream of each water quality monitor. So we had a dummy variable for each of the depending on the contaminant, it was several hundred water quality monitors in the study. And also each month of the study between January 2000 and December 2011. So I was very sure, right, that anything that was affecting average levels of contamination at that monitor, right, and anything that was affecting average levels of contamination across the whole set of monitors in any particular time period was well controlled for. Okay, so that's what I do with those dummy variables. And then ultimately I can still recover, okay, well, what fraction of that variation was from road salt, right? I can try and get at that, but I know at least in that first stage, right, I'm not sort of contaminating my estimate of the impact of shale gas development. Another sort of a similar thing is, so I have another piece of work going on right now with Hilary Sigmund at Rutgers, where we're looking at what's the impact of drought on economic activity using the nighttime lights index, right? Nighttime lights from space is the measure of economic activity. And then what's the mediating influence of dams, right? So I want to know, this is sort of a follow-on from the damming of international rivers work, where I'm trying to understand, maybe I've got drought, and if I have a dam in Ethiopia that makes things better locally for Ethiopia, but it might make things worse for Egypt, right, which is downstream of Ethiopia on the Nile. So we want to do that, right? But again, right, there's all kinds of things about, right, every particular location that I might worry about as a driver of economic activity, and frankly, suitability for damming, right, and other things that I might be concerned about. So what do I do if I'm using this very flexible approach? Well, I take each sort of 10 kilometer by 10 kilometer grid cell in the study, and I create a dummy variable for every one of those, right? So I say, whatever kind of the, in that location, whatever is the probability the dam is a good thing in that spot, whatever is the sort of local level of economic activity, I'm controlling for that, right? And the same thing with periods of time, right? This time we're looking at annual observations, so we have dummy variables for each year, similar to what we were doing before. So that's the general idea, right? This sort of very flexible set of controls. It's less descriptive, so what ends up happening, right, is that if I have a model where I've just got a whole bunch of fixed effects for monitors and years, and then, right, a variable that gives me a well count, right, and maybe one for precipitation, right, other stuff that varies over time and space together that could confound my results, I'm sort of not getting as much descriptive power out of that. It's sort of hard for me to talk to a hydrologist who's studied road salt, right, about what the impact, how and whether and how that's in my model, right? So we can talk about that later. I think that's an interesting question, how we talk to each other across these disciplines where we use empirical modeling. Okay. The second class of models are called instrumental variables models. And here the idea is, okay, I think that there's this problem with estimating this relationship of interest that can come from one of two things. One is something called reverse causality. Okay, so this happens in water demand estimation when we have these prices like most of us face, where they kind of go up depending on how much you use, right? So for your electricity or for your water, often what happens is, the first 5,000 gallons a month might, the utility might sell it to you at $1.50, but then between 5,000 and 10,000 gallons, they sell it to you for $2, and then it goes up to $2.50, and so on. And what that does is it says, actually, right, if I'm interested in an estimated demand function like the ones Jim drew earlier, I want to know kind of how does the price affect the quantity demanded. But if the price goes up, the more I use, then it's also true that the quantity that I use affects the price, right? So this kind of direct reverse causation. The left side causes the right side, and the right side causes the left side. So how do I kind of piece that out? So that's one source of sort of potentially damaging variation that would cause me to move toward an instrumental variables approach. And the other would just simply be that I think, I've got two phenomena, right, the right-hand side variable and the left-hand side variable, and they're both affected by some unobserved thing that drives both of them. That also can cause a problem, right, for my statistical inference. And so in both of those cases, I would go looking for what I would call an instrument. So what is an instrument, or set of instruments? It's a variable that's correlated with your treatment of interest, something like listing of endangered species, okay, or, the provision of information to households about their real-time electricity consumption, right? So it's my sort of correlated with my treatment of interest, but it should be otherwise independent of my potential outcome, right? So technically what I mean is uncorrelated with any unexplained variation in your outcome. And then you use these variables as instruments to first get an estimate of that treatment variable, right? That no longer contains the confounding variation, and then in a second stage estimates the effective interest. And I'll give you two examples where hopefully that will be a little more clear. The first one is a paper by Pitt and colleagues in 2005. This is still a working paper, so it's not a published paper, but you can find it easily online. And these guys are trying to estimate the impact of indoor air pollution, right, particulate matter, and that's their particular interest, from indoor cooking on women's health in Bangladesh. And they say, well, okay, again, kind of like the epidemiological story about water quality, right, there's plenty of studies that would show that, right, that indoor cooking fires damage health. But they say, well, that's true, but it's not as though households are completely unaware of this, right? And maybe they're kind of allocating intra-household allocation of cooking time, right? So that, right, the folks who are more likely to be exposed may already be, have lower health outcomes to begin with. Okay, so their story was, what they were observing kind of anecdotally in these households was that the sort of young mothers, with young kids would tend to do a little bit less, and the sort of older female members of the household were doing more. And so if you went out there and you just studied kind of, put monitors on everybody and kind of looked at what happened, if you weren't sufficiently able to control for these underlying health differences in who was doing the cooking, you might get this biased estimate of cooking on health. And so what they did is they used some instruments, right? They said, okay, I'm going to estimate, right, the sort of time spent cooking as a function of where I stand in the household, whether I'm the kind of wife of the head of household, the daughter-in-law, the mother, right, sort of my kind of different sort of familial relationship classifications. And then I'm going to take that estimate, right, of the sort of time spent cooking, and I'm going to use that as my right-hand side variable in the second stage, right? So now I don't have any of this variation in here, right, that has to do with my underlying health status. And so I'm going to use this estimate, and I have sort of greater confidence that it's an unbiased estimate of the effect. Another example, again, was this work on dams, looking at countries' propensity to dam international versus domestic rivers. And then there we thought, well, one thing that could sort of avert or at least mitigate some of that potential free riding behavior would be treaties. That's why we make treaties, right? Often over shared water resources is to figure out these water allocation problems and hopefully avoid some of these common property problems. But again, I have these two problems that I worry about with IV. One would be just that, once conflict has developed over a river or once a dam is kind of going into place, that's when I sort of go seek out my kind of other riparians to draw up a treaty. So one could be just this direct reverse causation problem, right? That sort of dams cause treaties and treaties cause dams. Another could be this sort of story that something that drives both dams and treaties, right, is not in my model. Okay, so I might have to worry about that. So there, what we do is we look at, okay, what drives treaties that has nothing to do necessarily, right, with water allocation in a river. It could be things like my sort of underlying propensity to cooperate with other countries. So maybe that is a function of things like my participation in international trade agreements that have nothing to do with water allocation, or my degree of sort of democracy versus autocracy, or these sort of political science indexes that capture kind of countries' sort of style of governance. And so again, there we take those kinds of variables, we use those as instruments to predict treaties, and then we take these kind of predicted treaties and we use them in that second stage. And so that's the general style of the approach. Then there are three different types, well actually there are many more than three, but there's a class of what we'll call difference in difference type models. And the first one is just pure kind of difference in differences. So that is, right, I have data on treated and control observations, both pre and post treatment, either from an experiment or from a natural experiment. I'm going to calculate the change in outcomes from the right, post treatment among the treated group, right, between the two periods, and then I'm going to subtract that from that the changes in outcomes among the control group. Right, I have changes in both groups over time, and what I want to know is what part of that change in the treated group is due to the treatment itself. So I subtract out that change in the untreated group. A second class of models are called matching models. So this you would have read about in the article by Paul Ferraro and Subrendu Pataniak, where you take you create your own control group, right? So what I do is I have a set of sort of treated observations, and I'm looking for a set of very similar, right, along a lot of different lines, observations that didn't receive the treatment, and I'm only going to compare those very, very similar groups to understand the effect of the treatment, right? So I'm kind of using these matches to statistically construct that counterfactual control group that I didn't observe. And again, I'll talk about examples of each of these. And then finally, there are regression discontinuity methods, right, where it's the assignment to the treatment is based on the value of an observed covariate, okay, so, and whether the value lies on one side or another of a fixed threshold. So in some ways, you think about that minimum wage experiment as a regression discontinuity experiment. What was the discontinuity? It was the state border, right? Sort of that determined whether you experienced the increase of the minimum wage or not, right? There are others as well. So a study that I worked on looking at what this impact of information disclosure on water utilities, a violation of Safe Drinking Water Act rules. The disclosure had to happen in sort of by size threshold, right? So for example, if you had more than 10,000 people that you served, you had to send out a report every year. You probably get these things in the mail. It's a little report from your water utility saying, hey, you know, these are the water quality tests we performed this year, and this is the violation we might have experienced. These are the health impacts, okay? And so what we did is we said, okay, there might be very different things about water utilities that are big versus small, right? So I'm going to control really flexibly for being big versus small. But if I take that threshold of 10,000 people, what really is the difference between a utility that serves 10,001 people versus one that serves 9,999, except for the fact that one has to disclose the information and the other doesn't. So if I can find a way to really just exploit that variation as close to that threshold as possible, that discontinuity, right, in reporting in my case, or right, there are lots of other examples, the minimum wage in the state case, then I'm exploiting variation that's as good as randomly assigned, right? I'm trying to make a convincing argument that that piece of the variation, like right around the threshold, is pretty much random. So let me give you an example of each one of those. So Laurie Bonnier has a paper in 2007 where she looks at whether a particular type of regulation called management-based regulation affects firms' releases of toxic chemicals, okay? And so she compares these kind of pre- and post-regulation differences and releases among plants that are covered by the regulations with the differences among plants that are not covered using that classic kind of difference in difference model. Paul Ferraro has lots of really nice examples of many of these different types of methods. The one that I'll talk about here is a matching paper. This was the Endangered Species Act paper, so the kind of heuristic that I was using in the beginning of this discussion, where he says, what's the impact of ESA listing on species endangerment status, right, using a particular measure of endangerment status. And he uses matches, right? So how does he match up, how does he come up with this kind of control group or this kind of created counterfactual? He says, you know, I'm going to take species and I'm going to match them based on taxonomy, size, their pretreatment endangerment status, the number of scientific publications that exist for each species, the League of Conservation voter score of state delegations where the species habitat is predominant, and these kinds of things, right? So I'm going to try and look for and kind of create this sort of fake control group, right? And then I'm going to run this test of, right, how listing affected the species that got listed versus these fake controls. And then finally, a good example of the regression discontinuity approach, other than the ones that I've described, is a paper by Ken Shea and Michael Greenstone in 2005, where they want to know what's the impact of air pollution, and in particular, they're looking at particulate matter, fine particulate matter, on housing values. So this is an example of a hedonics paper, right, that Pete was talking about earlier, right, this question of whether air quality is capitalized into housing prices. And that can be a little bit tricky to tease out. So one thing you might do is use a regression discontinuity design, and what they do is they exploit this discontinuity and the sort of stringency of regulation that occurs, right, when EPA sort of implements a sort of newly stringent ozone standard, a newly stringent standard for particulate matter. it affects communities differently whether if they're in attainment with the existing regulation versus if they're not, right? So more stringent regulations come into place in non-attainment zones, right? So it's relatively more costly, and communities have to do more, right? More testing or more whatever, right, in order to comply with those new regulations. And so again, this creates this sort of fundamental discontinuity between, right, and how communities are affected by the regulation just based on whether they're in attainment versus non-attainment, and they're able to exploit that to understand the impact of pollution on home values. All right. So in conclusion, right, so empirical folks like me who study these environmental amenities, environmental policy, we use these large-end statistical methods. It's very different from, right, sort of case studies or descriptive approaches that are used in other fields, but similar to what the kinds of tools that are used in other fields that use these kinds of methods as well. We call this econometrics, but the tools resemble those in other fields. In fact, when we look at the sort of evolution of this, kind of causality revolution in econometrics, a lot of those, the early papers that, you'll find cited in the economics papers using these came out of education policy. So education researchers who had used these kind of quasi-experimental techniques for a long time before economists even really kind of got wind of them. So we borrowed them from other fields. And Chris asked earlier in the discussion today, are we seeing these approaches used in other fields? And the answer is yes. And in fact, right now, if you Google instrumental variables in epidemiology, you'll find a really kind of healthy debate within that field about, gee, should we be using these methods? Should we be adopting them more closely in a lot of different contexts? And there's a real sort of debate going on within that field. So I would say yes, right? We're not the first. I'm sure we're not the last to adopt them. But I think an important difference, right, is this sort of emphasis on causal inference using observational data, right? Experiments are still the gold standard. We see more and more of those where they're possible. I think one thing to be cautious about, though, is that if you're really only willing to draw conclusions from true field experiments, randomized experiments, then you may be stuck only looking at the questions, right, that are feasible to use experiments to look at. And I think that's a small set of questions. I think we certainly have not fully exploited that set of questions, and there are more papers to be published in great journals using experiments. But I think if you're more driven by the question and less by the methods, that might feel a little constraining, right, to really just to do experiments. Again, that's because there are a lot of interesting and important questions that you simply can never, not that you couldn't design the hypothetical experiment to test, right, but that you just can't actually do the experiment, and that's quite constraining. So we've had to adopt, right, from other disciplines, and in some cases create new methods or sort of push them further to bring some of these qualities of controlled experiments to observational studies. And I think that's where we do differ, right? I think what happens sometimes in fields where there has been a long tradition, a much richer tradition of experiments, I think there's a willingness to sort of say, well, like this question I can really only tackle with observational data, and that can only go so far, right? I really can only understand sort of associations between one thing and another, and I really am not going to be thinking about causality because that's what I do with my experiments. Well, I think in economics, for most of the history of the field, we haven't done experiments. It's only really pretty recently we have, so almost always being stuck with observational data has put this field in the position where we've had to really try to squeeze as much as you can, right, out of these methods. And I think, to some extent, we're evangelists for these methods as a result of that experience.